and I'd like to say something to give an indication of how it's proved. And I've also got a feeling that I might have gotten the inequality in the theorem slightly wrong. So we have this bundle map. Which is covering, so F is a diffeomorphism. We know that fibers contracted by at least a factor of lambda, so which we can assume is less than 1. So the action of the fiber map on the fibers is Lipschitz with Lipschitz constant lambda. And then I think what I want to say is I want to assume that the base is contracted by at most mu, so that the distance, whoops, I don't mean the distance from x to y, I mean the distance from fx to f of y is greater than or equal to mu times the distance from x to y. And I'm mainly interested in the case where mu is also less than 1. If mu is bigger than 1 and the base is, well, gee, if the base is going to be the base map is going to be a diffeomorphism, you cannot, well, if the base is compact, you can't have mu bigger than 1. If you apply this theorem where the base is something like the unstable manifold, and it's able to just expand, then you could have mu bigger than 1. So I think if I have that situation, then the inequality that I want is lambda over mu to the theta less than 1. And I have a feeling that what I wrote last time was that, which if these numbers are both less than 1, doesn't really matter what theta is. This is going to be true. Well, theta is going to be positive. This will just be true. And so the problem was that the mu that I had yesterday is the inverse of the mu that, well, I think I inadvertently had the inverse of mu. So the mu I want to think about is this one, and this is the, so another way of writing that is that lambda is less than mu to the theta. And that's the correct, I think it's the correct inequality. And I think it's the one that's going to appear in the course of the proof. Let us hope. Okay, so I now want to say something about how you go about proving that things are hurled. So let me start with the kind of canonical hurled thing. There is y equals cx to the theta. So the idea is that this is hurled. The idea is that if I have a function that is hurled and the graph, and that's the point of the, and suppose the function is positive, well then the graph has to lie below this. And now if I think about the point xy on the graph, and if I have a mu that is less than 1, and I look at mu x, what's the corresponding point element? What's the corresponding height? Well, you get c mu to the alpha x to the alpha. So this is equal to lambda y, where lambda is u to the alpha. So that's a picture of the kind of canonical example of Hilbert continuity. And so now suppose I have a map, say sigma. Actually, this is going to be from yes?
Typically, theta would be less than 1,
Typically. Well, what?
I mean,
I guess I really should have.
Yeah.
I'm a bit silly. I should have drawn the graph in that way.
Right.
Well, I think the picture makes perfectly good
It's
sense whichever way, but you're right. This would be a more suggestive way of drawing it. Actually, you could also draw the case where the graph looks like that. That's Lipschitz. And in that case, lambda is just equal to mu. So this is the theta equals 1. That's the Lipschitz case. So, suppose I've got a map and I want to show that it's Hilbert continuous. What I will end up wanting to do is to show that what I want to do is to look at the ball around some point x. I want to suppose that there are, well, first of all, I can start off by assuming that sigma maps the ball of radius r around x to the ball. And this is just going to be Hilbert continuity at x. So I'll choose some suitable numbers, little r and big R. And then we also want to show you want to know that for some mu and sigma, if I look at the ball of radius mu to the kr, I'll consider the case where these numbers are less than 1. I want to know that goes into the ball of radius lambda to the k times r. Suppose I have that set up. Well then, what you're going to get is that sigma is theta Hilbert. And theta is going to be log lambda over log mu, which means that lambda, theta, and that means lambda is mu to the theta. And that's exactly the picture that we've got over here. So this is the recipe for how to sort of find Hilbert continuity. And the idea of the Hilbert section theorem is that you've got exactly the ingredients for the recipe. If I have point x in the base space, and I've got my invariant section, I know if I look at some ball around x of radius r, what I want to do is to think about my Actually, what I really want, I think, is I probably want the ball around F inverse of x with radius r, and I apply big F to the top, little f to the base, and then I will get something. The ball of radius little r will map to something in the base, but it will at least cover the ball around x of radius mu r, and we will get, certainly the image of the invariant section will go through sigma x, and whatever sort of, well, we have a contraction by lambda in the fiber. So a naive idea would be, well, which is the way I've always naively thought, I just say, well, you've got some box here, and the corresponding box, whoops, that I get over here, if I sort of have some radius big R there, I'm going to have radius lambda r here, and I've got the kind of setup that you see here. And if instead of going back one step, I went back 2 steps, I would come forward. I would get at least the ball of radius mu squared, and I would have a box that would contract, would be lambda squared. So, and then our hypothesis is exactly that lambda is less than mu to the theta, and that's going to give us theta-Hilbert continuity. So, if lambda is less than mu to the theta, we're going to come out with Hilbert continuity. So there's one thing that I've overlooked in what I'm describing, because what I'm describing would work sort of I've ignored the fact that my box, when you look at the big F acting on the box, sure, it contracts all of the fibers, but it also takes the sort of middle of the box, center line of the box, and does something to that. So the picture, sort of, if I knew that sigma was just constant, I would see the box collapse as I've described it. But of course, life isn't quite that simple. And so you have to also take into account the fact that big F is going to take something that looks a horizontal section and change it into something that isn't horizontal. So you have to be a little more careful in estimating what happens to the box. So I think really all I have to do is think about if I have maybe concentrate Y. Suppose I have a box here. Suppose there is sigma of Y, and this box is the ball around X of, say, radius R cross over Y, times the ball around sigma Y of radius R. What happens when I apply, let me now apply big F correctly to this picture? Well, I have to think about what happens to the horizontal section. It goes to something. And in the course of, in the statement of the theorem, I forgot to mention the assumption that big F is as Hilbert continuous as we're hoping that the section is going to be. And we need to use that assumption. So we can choose some constant little c with the property that if little r is small enough and the distance from y to y dash is less than r, then if we look at the distance from f of y something, or something, let's have something in the fibre, let's have say a in the fibre of y prime a. So we have this horizontal constant section of fibre. I want to know that this is less than or equal to c times the distance from y to y prime to theta. So in my picture, I know that by the time I've moved, I've got f of y there, and I want to look at what happens over the ball around f of y of radius, mu times r. So I think I go out to, so I know that the sort of vertical movement would be at worst c times mu times r. And then if I have my fibres with radius big R, the images of them have radius at worst lambda times big R. So I end up knowing if I take the box around the ball around f of y with radius c mu r plus lambda times big R, this will be big enough so that the graph of sigma stretches across the box. That's the product of this ball with that one. And then what you do is you just make sure that big R is much bigger, is big enough, so that the lambda R dominates this term.
Sigma of f.
Was it?
The sigma there.
Sigma.
Sigma of f.
F of y.
Yeah. Yes, sigma of.
Actually, f of sigma y.
Is that right now?
Point to the section above.
Yeah, so I want to take the
Point B.
yeah.
No, the one above.
So I want the
This is the
midpoint
product
of
of these two points.
yeah.
That one is up.
Let me. So the center of this ball should be sigma of f of y, and then I have to take a radius that's little c times mu r plus lambda times big R. So that's the sort of scheme. So I think I want to, now when I do that, I think I want to take big R to be some C0 times little r to the theta. Yes?
So it seems, I mean, this would work even if you don't have a smooth bundle, if you have metric bundle, where the trivializations, the transition maps are bidirections.
I
Then
think
this should
so. Yeah.
Because essentially, you're using, I mean, one trivialization, and if you change it,
Well,
you need the transitions to be bidirections for the same estimates to work.
Yeah. So I think if I have the sort of smooth bundle, the kind of bundle that you would have
Then
in
the
the Anosov set.
trivializations are pilot shapes.
Yeah. So the
Change of charts.
yeah. So in the case of the Anosov set, where you've got something in a fold, what I can do to I can either
I'm
use
just saying because
Yeah.
you know what Laborie and Canary and these people do, they have these metric Anosov flows where the spaces are not manifolds.
Okay.
They're still metric spaces.
yeah.
The leaves of the stable Anosov
So
affiliation.
Imagine you can do
So,
much the
yeah.
same thing.
Appropriate.
Yeah. So I
They
think
do
I
it in a metric way.
yeah. So I think I want to take I want to arrange the relationship between the sort of ball that I take in the base and the ball that I take in the fibre is something like that. And I want C0 large. One thing I want to make sure that it's big enough so that the picture of the graph of the section looks like that. So I make the little r small enough and the C0 big enough. And the other property that I need is I'm going to need, when I work through what I've got up there, I'm going to have C times mu times little r plus I now have lambda times C0 r. I've done something wrong. This was filtered continuity. There should be an r to the theta. And I think I can, my mu is less than 1. So I'm just going to ignore that. So if I take, I want to have C r to the theta, and then I have C0, lambda C0 r to the theta. Yes. And this looks like little c plus. Wait a minute. No, I do want to. Sorry, I don't want to leave this out. I do need to put it in there. I have C mu to the theta. So I get C mu to the theta plus lambda C0 times r to the theta. And now,
Like C plus C0 into lambda. Into the theta is equal to lambda.
yeah. Now what am I trying to remember what I'm trying to do? I want to I think I want to choose this so it's less than I think
Lambda r.
So then you need to choose that it's less than one.
lambda. I've got C, mute. There should be C. No, I think I do want to go, I'll have mu less than 1. I think I want C to the, I want C out of the theta. So then I will have C out of the theta. And then I get a lambda times BC0 out of the theta. And I would like to have that less than mu to the theta times have this less than so I now want to have this less than C0 mu to the theta times r to the theta. That's what I'd like to have. So that I then have the same. So I then have the same. My new ball here is going to have radius mu times r, and I want to have the same setup on this side. So I want to achieve this inequality. So I want C plus lambda times C0 less than mu to the theta times C0. And we know that mu to the theta, by hypothesis, is bigger than lambda. So if I make C0 big enough, this is smaller than that, and the gap is big enough that the little c doesn't matter. So so basically all that you're doing is that you're arranging that this box is long enough in the vertical direction so that you can effectively ignore the fact that the image of the centre isn't constant. It's not quite constant, but when the fibre contracts by a factor of lambda, which is a little bit less than mu to the theta, and the little bit less covers the fact that the image of the centre isn't exactly horizontal. So that's the idea of how the Hilbert section theorem goes. Okay, so that is the Hilbert section theorem. Okay, so now I want to talk about absolute continuity. Right. And so in the end, the only difficult step in applying the Hopf argument is to show that the foliations that you deal with are absolutely continuous. So the idea of absolute continuity is that I have a foliation W, and I look at some reasonably local picture, and then I have a set A, and I want to make an estimate of the measure of that. If I have a C1 foliation, I can do, or if I have a standard foliation, I can make an exact calculation of the volume of A, but I'm not going to. I can't expect to do that, but I sort of imitate what I would do in the standard case to find the volume by, I guess in the end it's really the area under the graph by integrating the height. So I pick some transverse, and then I can create a measure on the transversal. And you do that just by projecting volume to the transversal. So I look at my whole local region, project a volume to there. And then I would like to say that the measure of A is approximately the same as doing an integral over the transversal. So the integral over the transversal will be with respect to this measure mu. And then for each y in the transversal, I have a leaf, and there will be a measure on that leaf, and that leaf is just, we have some background geometry. The volume is the Riemannian volume, and on the leaf we have an induced Riemannian metric and an induced, so mu W is the volume for the induced Riemannian metric. On W. Okay, so that's our measure, and then you just take, you integrate the characteristic function of A, maybe with respect to something. So perhaps I can write the integral as the integral with respect to nu of mu W sub y of A intersect W of y. So you look at the volume at the sizes of the intersection and you integrate. So if you do this with the standard foliation and the standard measures, you get the volume. What we hope to get here is something that is approximately the volume. So absolute continuity would mean that the ratio of these numbers is bounded above and below. And well, obviously if you do this for big sets, you get such a bound. The point is that the bound on the ratio should hold no matter how small the set is.
Yeah, so again, given a transversal measure,
Yeah.
By the decomposition of measures, you get conditional measures.
Yes.
If the foliation is, let's say, smooth, then the conditional measures will have smooth densities with respect to the volume.
Yes. I'm not
They
saying
won't be equal to the volume.
Indeed.
They'll have densities with respect.
right. So you can. So if you just have a measure on transversal and a measure on the transversal, you
get
can
conditional
do a
measures.
decomposition. You get conditional measures. These conditional measures may be extraordinarily unlike the measures I'm talking about
Yes.
here.
But they'll have, if the foliation is nice, they'll have smooth densities.
Yes, so if the foliation is smooth, indeed, you get smooth densities, and this sort of business will work. If you try this with foliations that are not smooth, it may not work.
They'll be singular with respect to.
Yeah, and the picture that example of Milner
Will be
shows
singular.
that they can be incredibly singular. So in Milner's picture, if you decompose the Lebesgue measure into conditional measures on these curves, the conditional measures are all atomic.
Atomic, yeah, that's 1 point.
Yeah. And that is as bad as it gets for what I'm trying to do. I'm saying really that that the conditional measure should be absolutely continuous with respect to this. That's what I want.
That's the remaining.
Densities are bounded away from zero and infinity.
That's what.
Yes. Yeah. So I mean,
Well, that's strong.
Yeah.
I'm just saying.
in fact, I would.
Densities exist means they're just in L1 locally.
Yeah.
But actually,
Right, I
densities are bounded.
I want-
above and below.
I want to know that.
That's strong.
I want to know that the conditional measure, the radical negative derivative of it is between
1
1 over C and C,
Right, yeah.
and I want a C that works.
Which is the strongest.
Yeah.
Yeah, and I would also like to know that the C that I get depends in some reasonable way on the transversal and the size of the picture. So that, I mean, if I have some picture of my transversal is not very transverse, it starts looking like that, certain constants are going to get worse, and they should get worse because I've drawn an awful picture. But if I draw a reasonable, so in any reasonable picture, in some sense that I'd rather not try to make precise, but you can sort of figure out what it means, some sort of bound on the angle between the transversal and the leaves and things like that, I should get a uniform bound on this ratio. That's the kind of thing that you want. And so, okay, we've seen Milner's example.
Yeah, the estimate densities of normally it is with element densities. Or none of them.
So let me draw a picture in which this kind of thing is not going to work. To start, I want to have the square. So, Milner provides an extreme picture where it doesn't work. Here's a somewhat less extreme picture. I can divide the square into thirds. And on this, this transversal, I want to pick out the usual middle third Cantor set. So you remove the middle third, and then you remove middle thirds, and you keep doing that. On this side, I want to put what's called a fat Cantor set. I could start by removing the middle third again, but then I remove something from the middle that's quite a bit thinner, and I keep removing thinner things. And if you do a fairly easy calculation, you discover when you construct the middle third Cantor set that the total length of the intervals you've removed is 1. So the Cantor set that's left has measure 0. Over here I contrive that the total length that I remove is less than 1. So you're left with a positive measure set. So you have some Cantor set. I'll just mark a few points in it. And over here you have Cantor set. And there's a natural homeomorphism between the two Cantor sets. You can see how the top half of this picture matches the top half of that picture, and so on. So you can join matching points of the Cantor set, and then that will give me a collection of leaves of a foliation. There will be gaps, like there will be a gap in the middle, bounded by 2 of those pink leaves. Well, in the gap, I just sort of do a linear match-up of the 2 intervals. So I'm going to have probably something like that. And then I can just extend all my fibres, all my leaves horizontally in the left and right ends. And then you can see that this kind of thing that I want to do is not going to work, because if I look at a set over on this side, which is the fat Cantor set across this interval, I've got certainly positive measure for it, and when I come over to this side, I've got measure 0, and so if I use my transversal over here, my volume, no, actually, maybe I've done it the wrong way. I've done it the wrong way round. Well, no, when I project over to here, positive volume is going to project onto measure 0 of a transversal. All this kind of setup is going to go wrong. So that is another example of what we don't want. Okay, well, instead of absolute continuity, I want to have transverse absolute continuity. So the idea of transverse absolute continuity is that I again have my foliation W. I now have two transversals, T1 and T2. And again, these should be reasonable transversals. And what I'm going to describe will necessarily become, there's going to be a constant in what I'm about to describe, and it will necessarily become big if these transversals start becoming not very transverse. So we assume the picture looks something like that. And then what I want to do is to compare, if I have a set A in the first transversal, there is a Holonomy map for H, which takes sets in the first transversal to sets in the other one. So there's H of A. So you just follow weaves across. And now you want to look at the measure. You want to compare the measure, the volume of HA divided by the volume of A. And you'd like this to be less than or equal to J and greater than or equal to J inverse for some constant J greater than or equal to 1. And you want, well, obviously for any given set A, you do this with, you want A to have positive measure. For any given A with positive measure, well, I guess it's, well, okay, positive measure, it's extremely bad for what we're trying to do here if positive measure goes to measure 0. So we'll assume that that doesn't happen. But then you would still tend to expect that for, and you don't want measure 0 to go to positive measure, but you would still tend to expect that, well, J, you don't want to choose, you want J to be independent of A. You also want J to be independent of T1 and T2, unless T1 and T2 start becoming unreasonable. So you want a uniform constant that works for all measurable subsets of all reasonable pairs of transversals. That's transverse absolute continuity. And then the idea is that transverse absolute continuity implies absolute continuity. And so let me try to give a sketch of why that is true. So I have my foliation W, which I assume is transversely absolutely continuous. And then I want to introduce into the picture another foliation, which is, I don't want to have just T1 and T2. I want to have lots, I want to have a whole foliation by leads transverse to W. So we call that foliation V. So V is transverse to W. And we might as well assume that V, we could assume that V is smooth. I think it's enough to assume that V is, I think all I really need from V is that V is transversely absolutely continuous, but Anyway, I'll make V nice and smooth so you can apply Fantini's theorem and do the kind of things you want to do with V. And then now we want to think about, in this picture, I want to try to argue that W actually is absolutely continuous. So if I have some set A, I want to be able to estimate the volume of A reasonably accurately by integrating the measures of these intersections of W with A. And really what it's going to come down to is taking a small box which looks like the product of a set in a W leaf with a set in a V leaf, and understanding that we've got a reasonable estimate for the volume of that. So maybe I will move over here and draw a blown up version of that. So I have this box. And I have some base point P0. So this will be W P0, and here will be V P0. And then maybe, so this set here will be that set will be B, and so A sub Y will be, if I look at the leaf, it goes to the leaf, if this is W of Y, where Y is the intersection point there, so Y will be in VP0, and AY is the image of A in WY under polynomial along V leaves, and B sub X for X in WP0 will be the analogous thing. That must be in V of X and W column. Hopefully I've changed all the letters correctly. So this box, if you look locally, it really looks like if I've got sort of X, if I have X and Y, you can see that if I take the volume of Bx across the volume of Bx across Ay, that is going to be close to the actual volume of that little box. And now, what do we know? Well, I think really all we've got to do is observe. So if we, I think, yeah, I mean that's approximately the volume of the box, and if I do so, and the integral, and what I want for the absolute continuity to work, what I would need to know is that the volume of B times. So if I look at if this is my set A, the integrands here are all going to be pretty much the same as the volume of AY. And then the integral that I do is going to be over this set B. And I need a comparison of the volume of B with the volume of Bx over here. And in the sort of picture of the foliation that I constructed here, I can have a box over there. And by the time I've moved over to the transversal, the platinum box is wildly different. It can either positive height could collapse to 0, or it could go the other way. And in this picture, with the transverse absolute continuity, tells us that it really doesn't matter where we draw the transversal, we're going to get approximately the same height. And remember that this is supposed to work, doesn't just work for bigger sets A, it works for microscopic sets A, infinite, really infinitesimal. It doesn't matter how small A is. And so if you look at the picture of Milnor's foliation, you can kind of see how there are leaves that tend to get there apart here. And if you look at smaller pieces of it, you see even worse things like that. And the transverse absolute continuity says that that kind of thing is not happening. The foliation looks like nicely combed hair. But things don't collapse together. So that's a sketch of why it works. And I think
that indicates that kind of situation does not happen.
yes, yeah. And so really, it's clear that you can estimate that if you do this kind of estimate for the volume of just a tiny little box, it works approximately correctly. And then you just have to sort of integrate that fact. And I won't bother doing the integration. So transverse absolute continuity is what you really want to prove. So in the end, the main theorem of Anosov the unstable foliation say a C1 plus alpha diffeomorphism of a compact manifold is transversally absolutely continuous. So how do you do it? When you look at the unstable foliation, you look at a couple of transversals. Maybe I'll do the stable foliation. It's just a question of whether I apply diffeomorphism or its inverse. And I think I'll apply the diffeomorphism. So let's call the Anosov diffeomorphism F. And so the main idea is you apply F to the end to that picture, and your transversals stretch out a lot, and you're then doing polynomial over very short distances. And now what we're going to do, so we have in this picture, we have the polynomial map. And now we're going to construct a sequence of approximations. To H. And we will have that Hn converges to H uniformly. And we will also have that each Hen is well, I'll come to that in a minute. So the idea of Hn is I think of some map. I think of a smooth, I replace the actual stable foliation by something that is smooth. So so Hn is going to be equal to, I do F to the En, I do some H tilde, which is C infinity approximation to H, and then I do F to the minus N. That's Hn. And so, of course, if I put H in, if I used the actual polynomial along stables, I would get H back. But the idea is I go forward a long way. Instead of following the actual stable leaf, I follow something very close to it, and then I come back. And so it's easy to see that the error that I make when you don't follow the error that I make when I use the approximation to the stable foliation is small, and then I apply it to the minus N, which contracts tremendously. Yeah.
I mean, the proof of existence of stable and unstable foliations
Yes.
says that essentially if you start with a foliation, a smooth foliation,
Yeah.
which is almost tangent to the
Yes.
distribution,
Yeah.
then under iteration it's going to converge to the actual foliation.
Yeah.
So you
So
could take H tilde to be the holonomy of smooth foliation.
right. Well, I want
And then under iteration it's going to go back to, it's going to converge to
right. So
the
that
holonomy of the actual
yeah.
foliation.
So I have a smooth. That's essentially what I'm doing, and I think for simplicity, I might as well assume if I make each of these transversals be a WU, that will make my life. No, they can just be transversal. These transversals, I want them to be nice, will mean that they're reasonably close to being the unstable leaves. And when you apply the diffeomorphism, something that's approximately unstable becomes a better and better approximation to unstable. Yeah, so there's a step in the calculation that I'm going to pretty much skip. So maybe I will assume that these are actually the unstables. And so that, because I now want, so that's the construction of the approximating guys. Yeah.
I mean, the the Jurassic flow case, you could start with the foliation of the unit tangent model by unit tangent spheres.
I could.
And then that, as t goes to infinity, that converges to the spherical foliation.
Indeed. Well, pretty much any foliation.
Pretty much
any foliation
which
will
is
converge.
transverse, yeah.
Yes.
Any foliation which
Yeah.
is transverse will converge.
But there is a small step in the proof that I'm going to just wave my hands about. And if I use actual unstable foliations, that step isn't even there. So I will take some foliations some transversals that I really like. And now what I want to claim is that there is a constant J equal 1 such that if I look at the volume of Hn with A, it's less than or equal to J times the volume of A. Of course, a measurable set. And the point here, of course, is even for very small sets A. And this constant J is independent of E. So, of course, the independence of E is mainly what happens to B. And all you've got to do is realise that Hn is a composition of smooth maps. And so what I want to do is I just want to look at the restrictions of the derivatives to my transversals in the unstable direction, so to EU. And what I get is, let me call that J sub U, and you get J sub U of Hen is the compositions of derivatives the derivative maps do not commute with one another, but after I pass the Jacobians, things do commute. So this will look like what I have for H tilde times the product from K, times Ju of F to the En over Ju of F to the minus En. And this is bounded by something. But this is,
If you take minus N, then that should be on top.
maybe it's on,
divided
yeah,
by J.
it's one, yeah.
Otherwise, I mean, it's no, it's not that easy.
It's
the
making it
ratio
a product.
Jacobians are two.
Yeah,
nearby
I
points.
I think I need a product of this.
Yeah, that's okay.
So this is something that's just kind of bounded.
I mean, you can write it as the ratio of two Jacobians of F to the N at nearby points. Y and H tilde of
So,
exponential convergence
uh,
ratio.
well,
product will converge.
well, I've been a little sloppy here. What I really have is I have something like, maybe I should write out what I really have. I have something like, I start off with, I have X, which goes to I start off with X, and then I have X goes to Fx goes to F to goes, let's say, to y, and then comes back. It's called
H tilde of y. Equals to f to the n x is y.
what do I want to call this point? I do not want to call it y. I have f to the n of x, which I can think of as x e, and I'm going to call this point y e. And this comes all the way back to f to the minus n y e, which I will call y. And so each map up here is an f, each map here is an f inverse.
That should be just yn, right? Not f to the n of y.
Yeah.
The last just y.
Okay, well,
Yes.
yeah. Okay, this is actually f to the n of y,
Right.
which I call y.
Yeah.
E. So y is, no, yeah, y is maybe, yn is here.
Right.
Then there is actually h of xn. Yn and h of xn are reasonably close because these
Yeah,
leads are
Yn
extremely close.
That's h tilde of xn. Yn.
I want the actual horn on. Now this is
Is
h tilde.
Yeah, that's
But anyway, these points are very close, and when I start applying f inverse, they become closer. So what I really need to calculate is I want the Jacobian of, well, the J, I'll put the U up there, and this is, I want the JU at, I think it might be convenient to put XE, XK equals F to the KX, YK is F to the KY. So what I need to calculate is JU at X. So this means that X is 0 is X, Y is 0 is Y. If I look at the Jacobians of these F's, I get JU X0 at F times JU X1 F times etc. Maybe I was right, it is a product. I have the product of K equals 0 to n minus 1, JU at XK, or JU for F XK. Then I have JU or H at XE. And then I'm going
H2 plus
H tilde, right?
H2, yes. And then I have the product from,
You could just divide by JU of FYK. That is.
well, I will have F again, and this will be also it will be F inverse at, this will be K equals 1 to E
K.
of F inverse at YK. And so what I will get is JU H tilde XN, and then a product, whoops, of JU FXK, the Jacobian for F inverse is the inverse of the Jacobian for F, but I have to go from YK, the inverse goes one way, and I have to go, I have to change the end where I start from. So what I will end up doing is I'll find myself dividing by that.
F inverse.
What's that?
F inverse working on
Well, I've switched from taking the Jacobian of the inverse to dividing by the Jacobian of f. And what used to happen at yk, so f inverse at yk is the inverse of f at yk minus 1. So I get a product like that. And this product is almost the product that I talked about at the end last time. What I had at the end last time was the product of J U F X K divided by J U. Let me maybe call that ZK, where Z is the actual polynomial image. And we saw last time that this product converges as n goes to infinity to some number. And the only thing we need to add to that is we have to compare. I've got to compare this with that. And well, if we look at the picture of xn here, the actual holonomial takes it to zn, the fake holonomial takes it to y. These points are close. As we iterate backwards, the distance between them shrinks exponentially. And the distance here is, this distance across here is already in the original picture. Oh, another thing I forgot to say about part of my two transversals being reasonable is that as well as being sufficiently transverse, they should also be at some reasonable distance apart. If I have two transversals that are far enough apart, the constant that I'm trying to find will get worse and worse. So we can assume that this distance is the big O of 1. That means that the distance in this picture is exponentially small. So these are already very close, and then as you come back, they get even closer. The already exponentially shrunken distance shrinks exponentially again. And then it's really not very difficult to calculate that this product are very close to each other. So we are going to get a constant. And then I have cheated somewhat in this argument by using the transversals to be actual unstable manifolds. If I use slightly different transversals as I iterate forwards, I'm looking at the action of the derivative on the tangent space to the transversal, and that tangent space converges exponentially to the unstable space. And so there's another level of approximation in this calculation. And none of these approximations really make any difference. So that is more or less how the argument goes. Let me just point out that in the course of doing this, there were certain assumptions about if we don't have uniform control of certain things, this argument gets into trouble. So the argument works by saying, well, we've got points that converge exponentially, and then once they're close, we have bound on things. So we essentially have a uniform continuity of the various objects that we looked at in the proof. And if you have that kind of uniform continuity, you can do this sort of argument. If you don't have it, you can't. And that's why you can't do this argument for Nosov diffeomorphisms, well, for geodesic flow where you've got no control over the derivative of the curvature. Because we have the derivative, in the case of the diffeomorphism, we have the derivative of the diffeomorphism at nearby points. And we need to know that we've got continuity of the derivative. That's also why I needed C1 plus alpha. I wanted actual Hilbert continuity of that. That's why I have to have 1 plus alpha here. If I go to C1, the proof stops. You need to have Hilbert continuity of the derivative. And if you've got a situation like the surface with the cusp and no control over the derivative of the curvature, you don't have control. Just because points way out on the cusp are close to each other, that doesn't tell you that the derivatives of the flow are close. So anyway, that's pretty much the main idea of the proof, and I think that's a good point to finish. So thank you all for listening to, I think it was 7 lectures, which is rather more than I usually give in 1 week. So thank you, everyone.
Thank you very much. Let's thank them.
So